Oh, thank you. Okay, I'll bring this over here. All right. All right. Well, welcome everyone. Uh, this is the next in the series of we were science assemblies, which are focused on science preparation. And today we will discuss galaxy science. So your two presenters will be Christina and myself. And let's see, let's start out with okay. Today's agenda. So announcements. We'll start with announcements. Then we'll have Christina will take over and talk about galaxy science with LSST. And then we'll have then I'll talk a bit about the data products relevant for for galaxy science. And then oh, sorry, this is a little we didn't update the slide, so we'll have a data analysis demo using both. First of all, with the well, Christina will show us a demo using the uh, uh, Jupyter notebooks, and I'll then follow with something on using the notebook aspect, and I'll do something on the portal aspect. So just to remind everyone, the Rubin Community Workshop has the dates of the Rubin Community Workshop have been announced, and registration is now open. It'll be run from July 28th to August 1st at the Marriott University Park in Tucson, Arizona. It'll be fully hybrid, virtual plus in-person, but the in-person limit is 250. Chrissy, could you stick the link to the slides in the chat? I forgot to do that.
Yes, we're good.
Oh, thank you very much. So you can click on the link to the registration to go for registration. Also, this was announced last week also, but there was a press release on the Rubin Observatory installing the LST camera on the telescope, and it's now undergoing cooling in preparation for first photon, which we in a few weeks. And then just to let you know that next week there'll be another science assembly. This time, next week will be time domain with LST. There's also a set of other, so we're in the middle of seven of these. We've had the dark energy struggling in today's galaxies, and we have a few more coming up. You're all definitely invited to attend these. They're very informative. Also, just following most Thursdays, I believe there's one today also. So mainly following this meeting, the Link Frameworks will be having office hours, and Link Frameworks is their mission is to enable scientists to develop scalable and productionized software algorithms in collaboration with the broader community for Rubin. So they are doing some very interesting things here, and you can they have a meeting just after our meeting today. Let's see. Show you the user. Okay, we also remind people each week we would like to remind people that you have an advocate known as the Rubin Users Committee. You can so they are soliciting feedback from the community about Rubin data products and the science platform, and recommending improvements in the twice yearly reports to the Rubin Observatory Rubin Operations Director. Of information for contacting them and seeing their website and their charge are all here. And the committee members are listed below. And then finally, if you're new here, if this is your first time attending, you're welcome. You're definitely welcome. We're glad that you're here. If you haven't already, you should request a Rubin Science Platform account via rsp.lst.io. Currently we have simulated data as part of the data preview 0. Soon there'll be a data preview 1 with real data from the commissioning camera. The user resources for DP0 can be found at dp0.lsd.io, and the individual DP0.2, which involves extragalactic and galactic objects, and DP0.3, which has solar system objects, are at sub pages you can find under dp0.lsd.io. And we have a new web page, a newly updated web page for scientists, for general information for scientists at rubinobservatory.org/for-scientists. And let's see, this will be useful later on, but you may want to, you may wish we should review for accessing the hands-on tutorial. You can, but we'll see that more that very shortly. But here's a nice reference. You have the Christina has posted in the web chat how to access these slides, and you can follow those. And you can always ask questions in the chat. Oops. Oh, and then yeah, finally, when you do get to the tutorial, you want to use the recommended weekly version of the software and a medium size server. Okay, and then actually, okay, Christina, would you like me to just you could tell me to I'll hand it off to Christina. Would you like me just to kind of show the
Yeah, I'll let you know when I'm ready to change slides. Okay, so I'm just going to overview very briefly the sort of the areas of galaxy science where LSST is expected to revolutionize our understanding of galaxies. So just for sort of overall context, the really deep and wide area data coming from LSST is going to be a lot more amazing than what we've had before. So on the left, for context, I'm showing a picture of the Sloan Digital Sky Survey. The depth is about 22.5 magnitudes. On the right is an image of similar depth to a single LSST exposure, which is 24.5 magnitudes. And so for context, the final depth is expected to be around 27.5. And so this is like many magnitudes deeper than what has been available before. So this new unprecedented depth at wide area is really going to open up massive discovery space for the first time. Okay, next slide. So we have an LSST Galaxy Science Collaboration, which is taking new members. You have to have LSST data rights, but you can apply. Anyone is welcome to join with data rights. So you can apply at the link below there, which is the website that hosts the Galaxy Science Collaboration information. So the galaxy science that LSST is expected to revolutionize sort of spans a number of different pillars. And a lot of them are overlapping. So I'm going to try to go through a few of them that cover all of these different pillars in a minute. But I just want to highlight that there are active working groups within the Galaxy Science Collaboration, and this is a great place to network and build new collaborations and sort of get involved in what's already going on with preparation for LSST. So I've listed some of the ongoing working groups, and you can find more information about this at the website for the science collaboration. Next slide. Okay, so one of the things that LSST is going to revolutionize is probing a new wide dynamic range in both cosmic volume and across redshifts. And so the plot on the right here is showing sort of the cosmic volume for an L-star galaxy, which is sort of a typical brightness galaxy, as a function of redshift. And so there's a number of other surveys that are plotted here, but you can see the LSST is going to new depths in areas that have not been seen before in previous surveys. So we're expecting to probe the widest cosmic volume ever between redshifts out to even 5 and 6. And so this is going to really dramatically expand the possibilities in terms of probing the rarest cosmic environments over time, finding the most luminous galaxies across cosmic time, and also the most massive, supermassive black holes, and sort of understanding how the dark matter structure in which galaxies form is influencing the formation of these very rare cosmic environments. So there's a lot of stuff that falls into these categories that's going to enable all kinds of clustering analysis to understand the dark matter halos of the and probe the galaxy halo connection and sort of understand better how dark matter is shaping the evolution of galaxies. Okay, next slide. So another area where LSST will revolutionize galaxy science is by probing to very low surface brightnesses. So just as one example, the top left two panels are showing an object from Sloan on the right, and then the same object in an image that is of similar depth to the LSST data. And you can see these low surface brightness features just popping out, and this galaxy is not just a little blob, but in fact has all of these tidal streams and structures around it. And so this really encodes a lot of the hierarchical nature of how galaxies evolve. And so this is going to open up a new window into better understanding how mergers and other things contribute to galaxy formation and growth. And another thing that it's going to do is also better understand the dwarf galaxy population. So on the right, I'm showing it's just a simulated LSST image showing injected light profiles for dwarf galaxies at a range of luminosities to very faint luminosities and also to very large distances. And so you can see that LSST should be able to identify these very low surface brightness dwarfs across a range of parameters. And so we're going to get a much more complete understanding of the dwarf population in the nearby universe. Okay, next slide. So we talked about strong lensing yesterday. I just wanted to point out that strong lensing is going to dramatically expand galaxy science as well, in addition to better understanding transients and other dark matter related science. And so in particular, LSST is really going to dramatically expand the number of known lensed systems of various types. So we're going to find a lot more galaxy clusters across redshifts. We're going to find 100 times more galaxy lenses. And so there's some plots up here on the left showing just sort of the expected number of lensed systems of various types as a function of limiting magnitude. And so one of the key features of the LSST data is the higher angular resolution than was previously possible from such wide area surveys. So on the right is showing a Sloan image compared to another image of similar angular resolution to what LSST will provide. And you can see that this lens system splits nicely into the lens and the source. And so we will better be able to identify objects like this where we can both understand better the dark matter distribution in galaxies, but also discover new laboratories for galaxy astrophysics by studying the lensed sources in the background. Okay, next slide. Another thing is special populations of galaxies. So in particular, rare, massive, and bright objects that you typically can't find in small area surveys. And so in particular, the infrared filter available on LSST is also a new parameter space that will expand redshift ranges for wide area surveys. And so here on the left, one example is old quiescent galaxies at redshifts are up to about 2. Star-forming galaxies and quasars up to about redshift 6 to 7. So these are just SED models of typical objects compared to where the LSST filter set and depths are. And then on the far right, I just want to point out that distant galaxy clusters will be discoverable by LSST data, even in single LSST visits. So this plot is an old plot from existing data, but it's data that to a depth of a single LSST visit. And this is a galaxy cluster at redshift 1.3 or something. So you can see here, this is a color magnitude diagram where the red galaxies in this clusters tend to have a lot of red galaxies composed of old stars. These red sequence galaxies pop out easily in a color magnitude diagram, and it enables the discovery of clusters, but also the study of the cluster galaxies themselves. And so we'll talk a little bit more about this later in the tutorial. Okay, next slide. So one last thing that I think is worth mentioning about galaxy science, I think this new dramatically wider and deeper data than was possible in the past is going to really advance our methodologies for studying galaxies. So I've listed a few of the things here that are ongoing efforts within the galaxy collaboration. So there are efforts to develop new deblending techniques that are, so on the left in the top right subset here is showing a Hubble image, but on the right you can see the sort of slightly lower resolution of the LSST data, but this poses a new challenge for us to be able to identify Deblend galaxies, as you get to these very deep limits, galaxies the low surface brightness starts to blend together. And so there are ongoing efforts to develop new deblending techniques for this. There's also a need for expanding automated tools that can classify these pixels with flux and associate them with their host galaxies, and also to study the morphologies of all these galaxies that we're going to find in a more automated way. And so there's like some efforts going on in the science collaboration that you can get involved with to sort of learn more about these efforts, but also to develop new ones. And then there's also morphological and merger classifications that are ongoing. And this is an exciting application that can be used also for deploying these analysis tools with citizen science interfaces so that we can sort of harness the power of the public in understanding these very large data sets of galaxies and how to classify them. All right, so that's kind of a very very shallow overview of galaxy science that's expected with LSST. So I think now I'll hand it off to Douglas, who can tell you about some of the data products that are relevant for these analyses that will be produced in the data by the LSST pipelines.
Okay, thank you, Christina. Let's move on to data products, which are really those which are of relevance for galaxy science. So here we have a link and a link to the various planned data products for Rubin. For galaxies, is pretty much static science, not necessarily transient science. We'll talk about a transient science will be discussed at next week's session. Uh, uh, there are a few important data products. First of all is the deep coad, the coadded images. So these will be stacked every year. Every year there'll be a reprocessing and a restacking of all the coads for release during the LSST. And then there's taking those coadded images and detecting and deblending those objects. And those go into what's called the object table. And then there'll be co-added force photometry which will provide color information and photo Z information. And as a sort of a foretaste, here's a simulated small part of the sky of the what we expect the 10-year coad for LSST would look like. Of course, there'd be like 3 million of these to cover the whole southern sky. So it's very very deep. Lots of interesting detail there. Let's see. One thing that always comes up from SDSS and Pan-STARRS, the Dark Energy Survey, and so on is just what fluxes or magnitudes do you use for galaxy science? So currently, what we recommend for total fluxes, which aim to approximate or model all the light coming from the objects. For galaxies, the fixed C model flux measurements are generally recommended for galaxy science applications where total flux are needed. For instance, for measuring the intrinsic luminosity or mass of a galaxy. We also have apparent fluxes, which are measured inside an on-site aperture, but not corrected but without an aperture correction, without the correction for flux that they fall outside. And these are optimized for other purposes, such as for measuring accurate light profiles or accurate colors. And in particular, although C model flux actually, as Christina has shown in her studies, I mean, you can deal with the C model fluxes pretty well. But the current recommendation is using that Gaussian aperture and PSF or gap flux, which is described by Quaken et al. In 2008. These do a kind of a Gaussian fit and a correction, an aperture correction of sorts. per aperture correction to calculate an optimal. There's different apertures that can use. We recommend the gap optimal flux generally for galaxy colors. Let's see, moving on. Okay, we're just kind of we're currently wrapping up DP0. DP0, part of the DP 0.2 data are available now, and these are simulated data of a 300 square degree part of the sky down to about 6-year depths for LSST. They're primarily cosmology oriented. They were developed as part of Data Challenge 2 for the Rubin Dark Energy Science Collaboration. In June or July, we expect data preview 1 to become available, and that is composed of data from the commissioning camera, which is a 9 CCD camera, maybe from the same CCDs that say the same CCD set as many of the CCDs for the main LCD camera, and these are based upon data from taken during October, November, December of 2024 of last year. Later on, there'll be data preview 2, which will contain LSST camera, the main camera, 189 CCDs worth of data, covering about 100 square degrees at 10-year depths in UGRIZY, and 1,000 square degree at 1-year depth in GRIZ. This is described in Sitcom Technical Note 5. And then eventually there'll be data release 1 of which will be about 6 months after that. And we have some more details here in this slide, which came from Rubin Technical Note 11, Table 1. So here we show the current data data products and the timeline for release. It's currently expected currently anticipated time of release. We currently have DP 0.2 and also DP 0.3. DP 0.2 has images and process images, co-added images, and source catalogs, and different images and different imaging catalogs. Data preview 0.3 just contains catalogs of solar system objects. The ComCam data, which were expected in June or July, to be made available in June or July, will contain raw images, process images for the individual visits, the individual exposures, and their source catalogs, the co-edit images and object catalogs, and it's sort of an extended goal, a stretch goal. There's hope to also provide source catalogs and different images and different imaging catalogs, and then about a year and next year data preview 2 with the LSAT CAM science validation data, and data release 1, the first 6 months of data of the LST and operations status. We expect sometime in late 2026 or early 2027, and then about yearly after that. Want more information about data preview 0? You can we have there are recordings and slides of looking forward to data preview 1 meeting, Zoom meeting from February 6th. And there's also a technical document on an interim report on the ComCam on sky data, which is public. And I think okay, and that actually brings us to the data access demos. I just want to note where to find these demos. And let me add this Let me grab stick this in the chat. Uh, copy link. Oops. Copy link. I'll stick this in the chat. If you have questions during the demos, please raise your hands in Zoom, and the host will call you to unmute, or you can also type in the Zoom chat and it'll answer your chat or raise it on your behalf. And we have a question from Dan, or comment from Dan.
Yeah, sorry, just one uh, correction, I guess. We don't recommend the hub optimal fluxes. They are slightly misleadingly named. Like it's meant to be an optimally sized aperture, but in practice they actually work worse than the fixed size apertures. So
Okay.
contemplating removing that column from the object tables entirely.
Okay, that's good to know. And I know you've also been working on the general Sursic profiles, and those are looking good for colors. The Sursic,
Yeah, those will be in DP1.
yeah.
But for hop, either the 1 arcsecond or 3 arcsecond apertures in practice actually work well for galaxies.
Okay. All right. Okay. Thank you very much. Okay, that's good to know. We'll need to correct this. Okay, thanks. All right. So let's see. Okay, so let me exit and stop sharing screen and hand it over to Christina uh for the for the for the first tutorial.
Yes. So if so it's not necessary to follow along in your own RSP account, but if you want to, um, Douglas has sent the link for the GitHub access, so you can access the notebook yourself there, either by cloning in your RSP account somewhere, or you can download the notebook and upload it to your thing. So I'm just going to log in and go through a tutorial notebook that is geared towards just sort of overviewing the data products that Douglas just talked about. So from the main landing page, we're just going to go to the notebooks aspect. And like he said, we should pick a medium-sized container and the recommended weekly image of the server, and then we're going to start the server up. So I'm going to go through the notebook here so you don't have to follow along in your own RSP, but if you want to, please let us know if you have trouble with that. And there's a number of other community science team members online that can sort of help with issues if they arise. All right. Loading a little bit slowly today. All right. So I am already in my directory where I have the latest version of this notebook. So I'm just going to bring this up. There is a lot of descriptive text in the notebook in case you want to run through this at a later time, and it still has sort of some of the narrative that will help describe what's going on in the notebook. So I'm just going to kind of jump through here so we make sure we have enough time. Oh, there's already a question in the chat. Oh, never mind. That's from Douglas. Okay. All right. So the point of this notebook is just to sort of overview some of the data products that you can find access to that will be useful for sort of general science with galaxy science purposes. So some of the things that we're going to overview are the deep coad images, which Douglas mentioned are the ones that are the combined co-addition of all of the LSST exposures. And then we're also going to look at the object table, which is a table of detected objects inside the deep coad images, and also a number of associated properties that come automatically measured by the LSST pipelines. All right, so the first thing we're going to do is just import some Python packages that will be needed for this notebook. And we're going to define some plotting defaults. And here we're going to use both the tap service to access the catalog information, and also we're going to use the butler, which is sort of the image. It provides data products, in particular the images we're going to access using the butler. And so we have a number of tutorial notebooks that are geared towards understanding how these things work, and so I'll refer you to those other tutorial notebooks about the butler and the tap service in case you want more information. But just for now, that's what the purpose of these things are. So we're going to define also a few convenience functions. So in particular, I'm going to define this make image cutout, which is just a shortcut for creating little image cutouts of the DP 0.2 simulated images. And this cutout is nice because the simulated images are quite large, as are the real LSST data images will also be very large. So it's useful to have a cutout tool for handling smaller amounts of data. Okay, so the first thing that we're going to overview here are the deep coad images. So the deep coad images are identified by a tract and patch that they are in the sky. So the LSST survey is divided up into these patches and tracts. And also there are 6 different filters. So in order to identify a unique deep coad, we have to give it the tract, patch, and the filter that we want. So we're just going to do that here and define this data ID for this galaxy, or sorry, for this for this one deep coad image we're going to access. So let's plot that image so you can see what the simulated image looks like. So that's what this is going to do. And so the LSST image format has a number of extensions associated with it that contain some metadata that's very useful for analysis. And so we have some other notebooks that overview all of these different things. And just for the sake of this shorter notebook with a science focus, we're not going to go through those. But in any case, there are LSST pipeline display tools that can handle all of this image format with all these extensions. And that's called AFW display. So throughout this notebook, we're going to be using AFW display. So I stored this image as this variable coad. You can access the extensions with various tags at the end. So in this case, we're accessing the science image, and so I've put coad.image into the display function here. So this is a full patch tracked deep coad from the simulated LSST data. And so this is a really nice image because you can see there's this really nice galaxy cluster in the lower right. And so both this notebook and the portal tutorial, we're going to talk a little bit about this galaxy cluster and use it for galaxy science demonstrations. So there's a number of other things you can do. You can get the WCS information from the co-added image. There's a number of pipeline functions that are useful for getting the metadata from these things. So this is printing the location of the origin of the image, and the pixel scale on the sky. And so we want to find out more about this galaxy cluster. So we're going to zoom in on it. And to do that, it looks like the galaxy cluster is centered around these pixel numbers for this image. So we're going to find the RA index center for this galaxy cluster by using this pixel to sky function. And that prints out this RA index. So throughout the notebook and portal tutorial, we're going to keep referencing back to the RA index of this galaxy cluster. So earlier in the beginning, we made a little function that can make a cutout of these deep coad images so that they're smaller and you can zoom in easily. And so we're going to create a cutout now. So we have a notebook tutorial that's dedicated to how the cutout service works. And so I'm going to not talk about that. But in any case, you can find this in our tutorial notebooks. I think it's tutorial notebook 13A. So making the cutouts sometimes, depending on how many people are using the Rubin science platform at the same time, that can be a little bit slow. So we're just going to wait for this image to load. All right, great. So we have this image cutout. So I requested that this image cutout be 0.05 degrees on a side. So here's the size in pixels. And now it's the same format as the deep coad image it came from. So we're going to use the AFW display to display this cutout zoomed in on the galaxy cluster. So you can see all these simulated galaxies. It's very nice. And so now we're going to combine this with the measured properties of galaxies that are contained in the object table. So just a reminder, the object table is a catalog of things that are identified by running source detection on the deep coads. And then the LSST pipelines produce a number of automated parameters that go along with those detections. Oops, I mean for that to be hidden. Okay. All right, so the object table, so the first thing we're going to do is just search the object table for galaxies that are in that galaxy cluster using a radial search on RA index. So I'm first going to grab the dimensions of the RA index dimensions of that cutout that we created so that we can do a query for objects in the object table that are contained in that footprint. So here we're going to just do a tap query. So this is sort of, you've seen these in other tutorials with us before. We're just going to query the object table, which is labeled here in the tap query. And we're going to look for the RA and DEC of sources, the X and Y pixel coordinates. And we're going to request that their RA and DEC fit inside the corners of this cutout. And then we're going to retrieve all the objects. Okay, so that was just defining the query. Now we're going to send that query to the tap service, and we're going to look at the results. There's 2,966 objects that fit in that have been detected in that little cutout. You can display them somewhere. Oh no, I guess I don't display them there. Sorry. Okay. What we're going to do instead is display the RA and DEC of all of the centroids of all detected sources in the cutout. So we're going to plot that little cutout again, and now we're going to mark a location on the image where the object table contains a detected galaxy. And so you can see all of these bright cluster galaxies are detected, and then there's also a number of much fainter sources that have been detected by the detection algorithm around it. So this is showing you that the object table contains the things that are also in the deep coad. So this is very nice. So along with all the RA and DEC of these things, there's also photometry that is automatically measured for all of the objects in the deep coad image. And like Douglas overviewed, we can now look at those photometric measurements and just sort of make some comparisons of those different photometric methods to each other and see how they compare. So there's a lot of narrative text here just to sort of explain what the pipelines are doing and also point you to other information if you want to sort of dive deeper into any of these things. And so I'm going to skip over all this narrative text in the interest of time, but it's there in case you want to go back to refer to it. All right, so the first thing I'm going to do is just print here to the screen the number of the different photometric measurements that are available, and you'll see that there's quite a few of them. So here I'm just making a query to the object table. I'm making a query to a catalog of the schema for the object table so that we can collect the header information, like all of the columns that are available in the object table. And then I'm going to print only the ones that have flux in it, which means they are measurements of the flux automated by the LSST pipeline. So here I'm just showing the I-band measurements, but each of the filters gets the same photometric measurements in the object table, but just showing one band shows you the unique different measurements that are available. And so you see there are a lot of them. Some of them are geared towards very specific cases. And so we're going to sort of overview some of the ones that are more generically useful for galaxy science. So here you may be familiar with simple aperture photometry. So it's just a circle that you plop down on the image and you add up all the flux that's present there. One thing that Douglas mentioned, these are not aperture corrected, by the way. It's not, if you're looking for a galaxy population where the sizes may be variable, then this isn't really a very, it may not be the perfect measurement of flux. So Douglas mentioned this C model, which is, I think it means composite model, and it's basically the sum of two Sersic profiles that are modeled to the galaxy's image. And so from there, you can collect that model will account for the full galaxy, the full light coming from the galaxy. And so this is sort of our best estimate of total flux. And then we talked a little about the GAAP. So maybe the optimal GAAP is not the best option for colors, but we are going to talk about it anyways in the course of this tutorial. And then also I'll point out cron photometry is also a very sort of standard measurement of photometry that's widely used in the research community. And so I just want to point out here that the cron fluxes that are in the pipeline are not aperture corrected, although they do have a variable aperture like the C model. Well, C model doesn't use an aperture, but it's flexible for the size of the galaxy. But the Cron photometry here is not aperture corrected, so that does mean that you won't collect the full flux of the object. All right, so I have a little bit of narrative text here that I'm just going to skip over in the interest of time, and we can discuss that later if anyone has any questions. So the first thing we're going to do is now take this whole galaxy cluster, and we're going to do a search query through the TAP service for all of the photometry measurements for the objects inside that galaxy cluster. So this is a query you can see here. We're requesting to get some of the flux measurements from this object. I've also attached here some of the flags associated with these measurements. So there's a number of quality flags you can use to sort of check whether or not the measurements are good quality or not. And then I also want to point out that there are some shape measurements available in the automated pipeline that can help you characterize the shapes of the galaxies and are used to construct the Cron apertures for the Cron photometry. So we're just going to run this query and retrieve some of these things so we can explore what they look like. Okay, so I ran this query and now we have the results in a table. So here you can see we have RA and DEC. We have some flags here for whether or not objects are extended, so we could remove stars and keep only galaxies in this. And then we have these flux measurements available. Okay, so I'm going to turn these fluxes into magnitudes because I think in magnitudes. And so you may too, but it's easier to see the differences in the fluxes in log space anyway. All right, so the first thing we're going to do now is just visualize what these photometric measurements look like on an image of one galaxy. So this is an object that is fairly large and elongated as an example. So I already picked out the ID, but you can also, adjust this and explore other objects by doing a different selection. So we're just going to wait for this. This picks out one elongated object, makes a small image cutout of it here, and then plots the cutout. And then this text here is just generating the apertures in photutils or something so that you can compare the different apertures. I also explain here a demonstration of how to reconstruct the Cron aperture in case that's something you're interested in doing, but I'm not going to talk about that too much. It's just I will point out that some of these parameters, including the way that the Cron size measurements are made, will maybe change their format in DP1, but this is we're plotting here what's available for DP 0.2. Okay, so here's an elongated galaxy from that galaxy cluster, and here I've plotted a few of the apertures available from the for photometry that's in the object table. And so you can see the Cron photometry does a good job of capturing the elongated nature of the galaxy, but it does lose some of the exterior flux from the galaxy. So it is going to miss some of that flux. And the same thing is true for these various circular apertures. None of these perfectly describe the photometry of the galaxy, which this is one reason why we recommend using the C model, because the C model is modeling the light profile of the galaxy in a sort of more independent way and in an automated way. And so you can get a better estimate of the total flux. So just as a demonstration, I'm going to compare this C model flux to the aperture photometry flux. So this is just a quick demonstration here by showing the C model magnitude, which we are saying is the sort of closest to the true magnitude of the galaxy, minus the aperture magnitude. So for each of these apertures, there's the red one's a very small aperture and the blue one is a very large aperture. As you go to smaller and smaller apertures, you will lose more and more flux of the galaxy in that photometry. So here on the x-axis, I'm just plotting the Cron radius, which is a gauge of how big the galaxy is. And so as galaxies get bigger and bigger, the smaller apertures are less accurate at measuring the fluxes. And so you can kind of see this demonstrated here. It's just to sort of show you that the aperture photometry is less accurate than the C modeled photometry. Okay, so I am now going to hand this off to Douglas, who is going to show you another application of galaxy science you can do with DP0 using the portal tutorial or the portal aspect.
Okay, thank you, Christina. Let me share a screen here. All right, let's see. Show meeting. Okay. Let me I'll just stick the location of my presentation in the chat. So we don't have a whole lot of time, so I may need to kind of trim some of this. But I do want to talk about uh, using the portal to compare the color magnitude diagrams of a set of field galaxies and a set of cluster galaxies, and basically to show how the red sequence kind of pops up uh, in a color magnitude diagram. So I put the link to this. I won't go into detail here. I did want to kind of show you uh, this nice plot here, this nice image here. So let's see, this is Abel 3158 taken by the DCAM, part of the DESI Legacy Imaging Survey. So it's not sure the exact depths or how comparable it would be uh, to 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 Rubin. I mean, Rubin will go deeper. I'm not quite to the depth here though. For this coad here. But okay, the field population contains a heterogeneous mixture of galaxy types, including spiral galaxies, irregular galaxies, and elliptical galaxies. And rich clusters are composed mostly of elliptical galaxies, which have very similar rest frame spectral energy distributions. So as a result, they look kind of, I mean, if you look at a cluster of galaxies, they all look like, all the galaxies look basically more or less the same color. And like we see in 3158 here, all these kind of yellowish white things are all part of the same, all part of 3158. You'll also see, if you zoom in close, you'll see things that are really red. You'll see here's one of the things over here which are really red. Those are distant. Those are galaxies much further away or more distant. More distant. There's also a couple of cases where you see something that's really quite white. That's probably a foreground galaxy. So can you kind of use the color of since this is a way of finding, this is a good way to find clusters of galaxies. You find things that are close on the sky. They all have the galaxies all have the same color because most galaxies in a rich cluster are ellipticals. They all look the same, more or less. Um, so let me yeah, so little time left. I will just kind of put this over here and kind of go quickly through this. I'll go to the portal, go to DP 0.2 catalogs. I can just follow right along here, very detailed. Uh, edit 80QL. So we'll like grab one of the 80QL. We'll execute this 80, we'll grab this 80QL query and we'll just stick it in there. And we will run it. And hopefully it'll come back pretty quickly. Yes, it did. You'd have about 29, almost 3,000 objects. This is within a 0.1 degree uh, uh, um, radius of a kind of a random location on the sky. So we're just looking at field galaxies. There's this active chart. There's this data product thing, which doesn't show anything. You can click over here to get coverage. That shows a HIPS map, imaging map, and then you have the table down here, and you have the 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 orange. You can click on things and click on things in the active chart. It'll be yellow, orange, and you'll get the highlighted thing down here. So we grab the object ID, the ARIAN deck, and the C model magnitude in IDAD, and the G minus I color in GAP. And using the gap optimal, which we don't, I guess shouldn't use anymore. But anyway, we use it here. It's good enough for the moment. Da, da, da. So I won't go into details about the proof. We have so little time, but we will we'll go to the active chart. We'll click on this little gear thingy, and we will let's see. We will select for the x-axis the I model magnitude, and for the y-axis the G minus I color. We'll change the chart options. We will, let's see, call this color magnitude random field sample, and we'll say, and we'll give the label IC model, and Y label, and G minus I gap. Uh, we'll add the grid for guiding the eye, and we'll kind of aim at I band from 16 to 25, and delta and the color of minus G minus I color -2 to 4, and apply, and we get this blob. So no nothing. It's more or less a blob. Now we'll just do the same thing. So this is G minus I versus, so faint, bright to faint, and blue to red on the y-axis. Well, let's quickly do the same thing, but for but basically same identical thing, except we will use a different coordinate that's aimed at a cluster. And actually, we can just don't even need to do this. We just go back here, change the ARIA index in this query, and do a search. And then we should have like what? Yeah, that's about right. That's 3,439 objects. We will go back to the active chart, click on click on the gear symbol. We will plot I versus G minus I versus I, and let's change the title, and the X label, and the Y label, and we will also do 16 to 25 in IBAN, and -2 to 4 in color. MSI color, we'll apply it. Let's close this. And we'll see that, okay, it's a blob, but it's a blob with a nearly horizontal line here. And that horizontal line, these are galaxies all the same color. That's the cluster. And if you want, you can click on one of these bright cluster galaxies, and you can go to the coverage, and you can just zoom in on it. The little crosshairs is the location, the center of the circle which we queried around, and the little orange diamond, crossed diamond, is the location of the actual galaxy that we have clicked on here. And if you zoom in really close, okay, so here's the cluster. And it's the same cluster that Christina showed us in the previous in the notebook tutorial. And actually that is basically it for details. You can you can do this on your own, following the instructions here. It's very step by step. And with that, I think we can open for a few minutes of questions. And let's see. Any questions? Oh, we have a, okay, thank you. That was a clap. Yeah. Apologies for the kind of rapid, there was a lot of material to go through. And so we had to go a bit rapidly, but I think all the instructions, we have detailed instructions in the slides and in the GitHub repo. Um, and yeah. Christina, do you have any comments or any things to
Yeah,
close
I
out comments?
I guess I'll make a comment sort of going off what Dan said. I think so this simulation was all DP 0.2, and I think the LSST pipelines are still in a state of development in some way. So the DP1 catalogs may be different than the DP 0.2 catalogs, that in that they will have different people will have converged on decisions about whether or not certain parameters should stay in, or new parameters be added. So I think stay tuned for updated tutorials once once DP1 is released. We're gonna update some of these photometry tutorials and to reflect the new catalog structure when that happens.
And Alan in the comments makes a good point, that good thing it's all recorded, and it is, and the recording will be posted I should be in the next couple of days. And Tom was wow, that's amazing. Tom was able to follow along. I'm not sure. I don't think I could have followed along in both the notebook and the Perl tutorial. So that's great. All right. I don't know. Christina, shall we well, let's see. Any final questions? Comments? Oh, Krishnan?
Hello, can you hear?
Yes. Yes.
Hi, yeah, thanks. It was all clear. I just want to ask, in the coverage field, there are a few numbers shown. Are these related to the tractor and the other ID of the images, or is it something different?
Oh,
The
yes, yes. Let me share a screen briefly. Where is that? So you're referring to the purple.
for you, yes.
Yes, those. Okay, I might need to defer to Melissa. I don't remember right offhand. I believe these are part of the how things are divvied up in the HIPS map.
Okay.
So I don't know right offhand. I should, but I don't. This is I believe
I
these
think
are
it's
not.
not. I mean, I also don't know what the purple refers to, but I know it's not the patch and tract, because the patch and tract we used in the notebook to find the image was not corresponding to these numbers.
Okay, okay. So it's not corresponding to the patch and tract. Okay, cool.
No,
That
no, afraid not.
thanks.
All right. Well, thank you for the question. And yeah, that's yeah. So we should look up.
No problem. Thanks a lot.
Okay, thanks. Anything else? Oh, and Melissa said also you can zoom in, and you also see the individual. Uh, oh, yeah, you can see the individual object detections and so on.
So I think the number she's saying, the number that is plotted there is the number of objects inside the box of the grid.
Ah, okay. Ah, okay.
Thanks,
That's
Melissa.
All right. Well, thank you, Melissa. Thank you, Christina. Thanks everyone. Yeah, so we're at the top of the hour. So thank you, everyone. Please attend future meetings. Next week's is on time domain. That'll be very interesting. And if you have any comments, please let us know. All right. Well, thank you very much. Oh, Christina, any last?
Nope, that's it. All good.
All right. Bye, all. Oh, we should turn
Bye.
off the recording. Whoever's doing that.